In this video, I want to build off of the 3 blue 1 brown video about eigenvalues and eigenvectors. So make sure you watch that video before watching this one. The animations that I can do are nowhere near the level that are done in that video, but hopefully I can give you some sense of this other very important related concept, which is not covered in the video, of eigenspaces. All right, so I have on the screen a definition of eigenvalues and eigenvectors. And in that video, the 3 blue, 1 brown video, where he talks about how eigenvalues and eigenvectors seem more complicated than they are, I think this sort of definition that I'm presenting to you is kind of part of the problem. If you feel like you understand what an eigenvalue and an eigenvector is, don't let this definition dissuade you from believing in yourself, right? All this definition is saying is that we're dealing with linear transformations from one space to a space of the same size. And for the purposes of this discussion of eigenvalues and eigenvectors, we're going to conflate the notions of a transformation and its matrix. So when we talk about the eigenvalue of a matrix or the eigenvalue of a linear transformation, they're the same thing. We're using them to mean the same thing. So the situation is that we have a linear transformation that sends a vector, a non-zero vector, to a multiple of itself. Equivalently, we multiply a matrix times a vector and we get a multiple of that vector. In that situation, we say that lambda, some real number, is an eigenvalue of the transformation, and that v is an eigenvector of the transformation with eigenvalue lambda. The idea of an eigenspace is to look at all of the eigenvectors that have the same eigenvalue. So when we have an eigenvalue of a linear transformation or of a matrix, the set of all eigenvectors with eigenvalue lambda, and we'll also throw 0 into that set, is the eigenspace corresponding to lambda. The idea here is that 0 can't be an eigenvector for good reason. Otherwise, everything would be an eigenvalue. But the 0 vector always satisfies the property that a linear transformation takes it to any multiple of itself because it always just gets mapped to 0. So the eigenspace is all of the eigenvectors of the linear transformation or matrix along with the 0 vector. So why is this important? Well, let's go to an example. So I already have example 2 up here. Let's just look at example 1. So example 1 is going to be an R2. And so this linear transformation has matrix 1 and a half, 1, 1. And I want to look at what it does to the standard basis. So it takes the standard basis and it maps it to this. I'm going to slowly add layers to this, this picture. So a linear transformation, based on where it sends the standard basis, we know everything about it, because if we add in some grid lines here, looking at where x equals 1, x equals 2, y equals 1, y equals 2. If we add in all these lines and we look at where these grid lines get sent, we can kind of see that the standard basis is forcing all of the other points in two-dimensional space to go to a certain spot. This is what we mean when we say that a linear transformation is determined by where it sends a basis. And the thing is, if I add in this special vector, put in actually 2 special vector, these are eigenvectors of the transformation, and we run the transformation again, what we see is that the blue vector is just getting shrunk by a half, or shrunk by 2, and the orange vector is getting doubled in length. So the blue vector has eigenvalue a half, and the orange vector has eigenvalue 2. And there's nothing, these are special vectors, but there's nothing special about the multiple I chose. So anything along this blue dotted line will be fixed by the linear transformation. Let's go back to where it's starting at the beginning. So these are my eigenvalues and eigenvectors. Anything along the blue line is going to get shrunk by a half, and anything along the orange dotted line is going to get multiplied by 2. So let's run it again. So the idea here is that these lines aren't being moved, and in fact, everything on these lines is either being doubled on the orange line or cut in half on the blue line. The orange line is the eigenspace corresponding to the eigenvector, the eigenvalue 2. Those are all of the vectors that have their length doubled by the linear transformation along with 0. And the blue line is the eigenspace corresponding to the eigenvalue lambda equals a half. Everything on that line gets chopped in half. Why is this useful? Well, let's get rid of the standard basis. It turns out that if we really want to understand this linear transformation, a good way to look at it is just to look at these two vectors. So looking at the linear transformation in terms of just these two vectors, it looks much simpler. It's just shrinking and stretching. And one thing I can do is, instead of having those kind of standard basis grid lines, I can throw in grid lines that line up better with my eigenvectors. So I can throw in grid lines that are parallel to my eigenvectors, and I can see what happens to those when I run the linear transformation. And what we see is that they're just getting stretched out or squished. And finally, just to show you that this really is what's going on, if I put the standard basis back on the picture, you can see, following where the standard basis is on the grid lines, how it is being mapped by this transformation. So I think the take-home message from this picture is that if we understand the eigenspaces and we try to study our linear transformation in terms of those eigenspaces, we have a much nicer picture of what's going on, as opposed to what we initially looked at, was where all we had was the standard basis, and all we saw was these two vectors kind of getting moved to some points, or these grid lines getting squished and stretched. Let's look at another example. So we're going to bump it up a dimension, and we're going to look at eigenspaces in 3 dimensions, because this is where things can actually get interesting. And they get even more interesting in higher dimensions, but we can't draw that. All right, so let's go into higher dimensions. So here I have this linear transformation defined by a matrix and some decimals, because I wanted it to kind of fit nicely into the screen. And here we have the standard basis showing up on our screen. And let's see what happens when I run this linear transformation. So this linear transformation sends the standard basis to these vectors. And let's look at an angle where we can see these a little bit better. I think that might be better. So let's start from the beginning. Our standard basis, and these vectors are kind of getting pulled back over here. So I can try this with grid lines, and we'll see what happens. So I did this, and I don't necessarily think this is a good way to look at it, because the animation just doesn't work that well. I threw in the same sort of grid lines that I had before. And let's see what happens with the grid lines. I'm not sure what's going to happen, if this is going to look good or not. I'm going to click, I'm going to play the animation. And so what you can see is that the grid lines are getting moved around by the transformation. And it looks cool, but I still don't feel like that's told me much about the linear transformation. So instead of looking at these grid lines, what I'm going to do is I'm going to look at eigenvectors and see what happens. So I'm going to put 3 vectors onto the screen, and I'm going to run the same linear transformation. And I left the standard basis up there so that you could see that it was the same transformation, but let's get rid of the standard basis and do that again, so that we can just focus on these vectors that I'm claiming are eigenvectors. So hopefully you can see that they're moving along the lines that they sit on, which is what is going on with an eigenvector, right? It's getting sent to a multiple of itself. And we can, if we throw an orange line on the screen, this line is representing the eigenspace. So that vector got sent to negative itself. So this orange eigenvector has an eigenvalue of -1, and this orange line I've drawn on is the eigenspace corresponding to the eigenvalue -1. Every vector that sits on this line gets sent to negative itself by the linear transformation. What's interesting is when we look at these purple vectors, because both of these vectors get doubled in length by the transformation. They both have an eigenvalue of 2. And the eigenspace corresponding to these is given by this gray plane. I tried to make it purple and it didn't look good. So let's run the transformation again from the beginning. So I have my eigenvectors on the screen, and I run this transformation, and you can see that these are moving like this. What's interesting is when we realize that if I'm claiming this is the eigenspace corresponding to lambda equals 2, that this gray plane consists of all eigenvectors with eigenvalue 2, if I draw another vector on this plane, I've thrown in this third vector, it should also just get doubled in length. And we can see that that's what happens. It gets doubled in length. So what's the big picture here? It's the same idea as with 2 dimensions. This linear transformation, initially, we just saw it kind of moving the standard basis to 3 new vectors, and we didn't really have a sense for what it was doing to space. And we drew in the grid lines, and we could see how it was moving all of space, but it wasn't really clear how it was doing that. But once we draw this picture, we can see exactly what it's doing. It's taking vectors on the orange line and reflecting them, or sending them to negative themselves. And it's taking vectors in the gray plane and it's doubling their length. And once it's decided to do that, if we remove one of these vectors, if we look at the 2 purple vectors on the screen, along with the orange vector, this is a basis of R3. Once we know that it's doing that, we know what it's doing to all of space. So this mysterious linear transformation becomes a lot less mysterious. In fact, what it's doing is it's kind of stretching out this gray plane by a factor of 2, and it's flipping things on this orange line, and then any other vector is just determined by this. And so hopefully you can see with this picture that if we want to study this transformation, it might make sense to study it in terms of not the standard basis, but these eigenvectors, because they give us a much better sense for what's going on. Okay, so hopefully that gives you a sense for what it means when we talk about an eigenspace and visually what they are. Right here, I think the nice picture is the gray plane, because, I mean, a single line is one thing, but this idea that when we have kind of higher dimensional eigenspaces, what we have is this subspace that on which the linear transformation is just stretching or shrinking or reflecting all of the vectors. I want to point out 2 more things that will be pretty quick, and I'll just go to only the Desmos screen for these because I don't want to put up the equations of the matrix. Eigenspaces are great. Eigenvectors are great. And if we have enough eigenvectors, if we can have a basis of eigenvectors, then we can really understand the linear transformation solely using eigenvectors. But we don't always have that. So this is going to be an example where I'll just run this linear transformation on the standard basis. We can see where it goes. And I'll add in the grid lines, because I do think that's a nice way in R2 to see what's going on with all of space. And then I want to add in an eigenvector. And I'll also draw in its eigenspace, or the eigenspace corresponding to that eigenvalue, and we'll see what happens here. And so we can see that there's an eigenvalue of 2, and it takes everything on that blue line and doubles its length. But it turns out that that's the only eigenvalue. And it's not even that. We'll talk a little bit more about this. Matrices can have complex eigenvalues, but this linear transformation, this matrix, the only eigenvalue is 2. But you can convince yourself it can't double some other vector that's not on this line, because then it would just be doubling everything in space, right? And it's definitely not doing that. It's changing some points in some other way. So this is a picture where what we have is a linear transformation that all of its eigenvalues are real numbers, but we only have one, or dimension 1 eigenspace. We don't have a full basis of eigenvectors. So we can't always just rely on having eigenvectors to study our linear transformation. This gets even worse, or I don't know if worse is the right word. Let's look at an example of a rotation. So here, where we can think of this as rotating the plane 90 degrees. And if you think about this, and I think this was mentioned in the 3 blue, 1 brown video, this definitely does not take any non-zero vector and send it to a multiple of itself, because it's rotating every vector by 90 degrees clockwise. And so this has no eigenvectors, although I will point out this matrix does have complex eigenvalues. So if we were studying this linear transformation in terms of a map from the complex numbers to the complex numbers, then all of a sudden we would have eigenvalues and eigenvectors. Okay, so hopefully that gives you a sense for what an eigenspace is. That was the main goal, but also why they're useful, that we can understand linear transformations better, and then some of their limitations. That is that we can't always expect that a linear transformation is going to have a basis of eigenvectors so that we can understand it as just stretching, shrinking, reflecting in certain subspaces that gets extended to the whole space.